Yeah, fine. Good evening, everyone. Let us start the session. Can somebody speak so that please let me know whether you can see my screen and able to hear me. And also, you can speak, unmute, and speak so that recording is going on, whether your audio is. Fine. Maybe this might be the last class of this phase. Uh, my class, I am telling about my session. Uh, because you will have gate on February 5th, right? Somewhere in February 5th, I guess. So before that, I'll try to take one class if possible, but otherwise, this will be the last class. Maybe all the best for your gate exam and do well. Especially before the exam from now onwards, you'll try to revise the topics and like don't try to learn new things now. Maybe if you have doubts and all, that is okay. Otherwise, don't try to learn new subject and all now. And whatever you have learned so far, like whatever you have prepared so far, just try to revise those things and uh, go for the exam. And in today's class, what we will do is like I think some of the students have asked from analog to digital converters and digital to analog converters, and also some miscellaneous questions from DFT, DFS, DTFT, jet transform they have asked. But in one class, we cannot cover all those things. I'll try to cover analog to digital and digital to analog converters and some of the previous questions. I'll try to cover as much as possible in this 1 hour session. I quickly will go through. So what I did was I wrote somewhere and I took the pictures of that so that I can cover more things in this, more content in this. So in today's session, we will see analog to digital converters. So A to D, analog to digital converter and digital to analog converters. And some of the previous questions we'll solve. First, we'll see analog digital to analog converters. We'll see, and after that, we will see analog to digital converter because ADC generally comprises of a DAC. So any analog to digital converter generally it will have a DAC, digital to analog converter. That's why first try to learn about DAC, then we'll learn about ADC. If you know any signal, let us say if you have some continuous signal, if you want to convert into bits, continuous signal, so what we do first, we cannot directly convert the signal into bits. Okay. So what the analog to digital converter will do, analog signal it take, the output is what, bits. So the signal cannot directly we can give. So what we need to do is first we need to pass this signal through a sample and hold circuit. Sample and hold circuit. Then what we will get samples. Okay. Some samples will get. Then quantization will be done anyway. Quantization, hope you know. After quantizer output, then we will give to a analog to digital converter. Okay, that means whatever we are giving to a analog to digital converter, not the directly continuous signal we don't give. We will give the sample only. The sample value is converted into in the form of some bits 0010 something like that. Okay, and let us say TS is the sampling interval. Okay, let us say to convert one sample, the analog to digital converter takes some amount of time. We say conversion time, TC, let us say. And So for successful conversion, the TS should be greater than or equal to TC. That means the next sample should arrive only after the complete conversion takes place. Okay, that means TS, the sampling interval, should be greater than or equal to TC. Greater than generally we take. Okay, right? Because it takes conversion, some time it takes. So this next sample should come only after successful conversion of the first sample, present sample. Okay, and this is overview of ADC. And once you have some bits, then let us say some bits, then we will use some DAC, digital 10 lakh converter. This we will say decoder. People they, ADC they'll say encoder, and DAC they'll say decoder. Then what we get is like samples. You'll get output of that is sample. Then the samples are discrete in nature. Then we have to use a reconstruction filter or low pass filter. Then from this a continuous time signal will get. This is rough overview. So each ADC in general will have a DAC. An ADC will have mostly will have a DAC. That's why we'll go through the DACs once. There are, I think you might have studied different types of converters are there. Some of them we will see. Hope this is visible for you, because to save time I just took pictures and kept here. So digital to analog converter, first we'll see in that different types are there. Primarily we focus on a binary weighted resistor DAC. You might have seen in definitely you might have studied, and R to R ladder DAC we will see. And after that, analog to digital converter ADCs will see counter type, successive approximation, parallel ADC or flash ADC will say, and dual soap ADC, sigma delta ADC, like that. Different types of are there. Maybe we'll touch upon first thing and the second, the third thing, and fourth thing. Okay. As I was telling, see here, let us say this is a counter. Just to understand DAC, this is a counter, let us say, and input at the clock, you are giving the clock input. Based on the clocks, number of clock pulses arriving, you will get the counter output. Bits you will get starting from 0000 to 1111 like that. And once you have reached, it's a 4-bit counter, so 4-bit counter. So 0000 to 00000 to 1111 or the output of the counter. Then again the cycle will be repeated. Now let us say now these digital inputs are given to the DAC, a DAC, digital to analog converter. So output is, let us say, V naught. Then equivalent a sample will be generated. Okay, let us say something called, we will say here, step size or resolution. Will say step size or resolution or delta. In terms of step size, the output of the DAC will be incremented. Okay, in output of the DAC will be implemented. Let us say the step size, we say 1 volt, for example. Step size is 1 volt. So when you are giving all zeros, the output is 0 volts. Let us say for all zeros, output is 0 volts. Now 0 0 0 0 1 counter is incrementing slowly. Then step size is 1, so its decimal equivalent is 1. So decimal equivalent is 1. 1 into step size is 1 volt, so 1 volt. Okay, after that 2, then 2 volts, 3 volts, like that. Finally 1111, so here what, 15 into 1 volt step size, so 15 volts. Again it is going to 0. Okay, this way we'll get the output of the DAC. Okay, so why we are getting some kind of some constant for some time, because that is the conversion time. On 0000, then before the next conversion took place, it will be maintained constant for some amount of time. These are like sample values. So here we have given an order, that's why they are incrementing this. Okay. So again, we will have LSB, MSB, and all. Now, we will see what is the resolution or step size. I said right, step size. This is also called as resolution. This is nothing but the smallest increment possible at the output of a DAC for any change at the input. Let us say you have a DAC here. So you are changing the bits here. You randomly change any bit. What is the smallest increment possible? That is the smallest one that can be incremented. Generally, it happens when all the bits are 0 and LSB you take is 1, LSB 1 and all bits are 0, then this is the least change possible, right? So this is nothing but step size. When all input bits are 0 and LSB is 1, then the whatever output is nothing but this is called step size. Whatever output we are getting, this is nothing but step size. Okay. And another thing called full scale reading, full scale output or full scale reading. When all the inputs of the DAC are 1, then output is nothing but the full scale output. Generally, it will be what? 2 power n minus 1. That many bits are there. 2 power 1 minus 1 into step size DAC. Step size of the DAC. You got it right? What is the full scale output? Let's say a 4 bit one. So 15 into step size. Step size is 1 volt. Let us say 15 volts it can go up to. You got it right? That is full scale output. And step size also called resolution. Sometimes they represent in terms of percentage of resolution. Percentage of resolution means ratio of step size into full scale output. Okay, step size is delta and full scale output is 2 power n minus 1 into delta into 100. This is called resolution, percentage of resolution. Now let us say how to choose a DAC. Which one is a better DAC? If you have given like this in terms of step sizes, zero point 0.1 volts step size, zero point 0.5 volts step size, 1 volt step size. Which one is a better DAC means which is having less step size, low step size. Okay, then the what to say, accuracy will be more. Step size is less means accuracy will be more. Okay, so for an n bit DAC, let us say for a 4 n bit DAC, how many different levels we will have means 2 power n minus 1 finite levels it can represent. So in terms of bits, number of bits if they're asking means the DAC with more bits will be finer. Less step size means you can have some smoother kind of thing. Okay, it's 8 bit, 16 bit, 32 bit. If you are given, then 32 bit will be the good DAC. Okay, so these kind of things anyway you have seen in encoder and decoder kind of things. Okay, so the corresponding digital decimal equivalent of the digital signal into step size is nothing but the DAC output. Okay, step size, that voltage. And now let us say one example you take. Let us say you take a 3-bit Johnson counter. The output is given to a DAC. Then how the output varies when you're applying clock pulses. The Johnson counter, you know, right? So 3 registers are in cascade, and Q naught output of the last one will be connected to the Q in input of the first one, right? Uh, input of the first one, right? So that is a Johnson counter. How many states will be there? If a 3-bit ring counter means 3 states will be there. Johnson counter means 6 states will be there. Hope you know this. Suppose if you're taking a Johnson counter, these are the different digital outputs of that. So accordingly, it varies the output at the counter. Just for understanding purpose, I explain this. Now, one of the, like I said, we will see two types of DACs. Till here, is this okay? Anybody is having any doubts? Quickly, I'll touch upon the things and solve some problems. Anybody is having any doubts? Fine. So first we'll see binary weighted resistor DAC. It's a binary weighted resistor DAC. So if you see here, here you have like op amp current to voltage converter is there, is an amplifier. Now you have minus VR plus VR depends if it is inverting amplifier, right? That's why minus we are taking. This is the reference voltage. Let us say it is 5 volts or minus 5 volts. And you have some switches here. S naught, Sn minus 2, like that switches are there. So it's a n bit counter. So sorry, n bit DAC, n bit DAC. It means obviously you know how many bits we have, like bits like so D0, D1 up to Dn minus 1, like that, right? So these are the switches. Based on the input is 1 or 0, based on the inputs will give here. Let us say you start from here A naught, let us say 0, an minus 2 0, an minus 1, or bits dn minus 1, an minus 1, whatever it may be. Based on this, the switch will connect this resistor either to minus vr or to ground, anything. If it is 0, particular bit 0, then connected to ground. Particular bit is 1, then connected to high voltage reference voltage. Now if you see here, these are the resistances. So these resistances, let us say this is rf, then the first resistance is 2 times of rf, let us say that is r. So next one is 2r, next one is 2 square r, 2 cube, or like that, 2 power n minus 1 into r. That is the output. Okay, 2 power n minus 1 into r. So these are the resistances. Now the resistance with lower resistance value, this bit corresponds to the MSB. This is MSB, low resistance value, and high resistance value. That means you see here 2 power n minus 1 into r. This is the LSB. Okay. So if you see here, these resistances, they are integral multiples of 2. R, 2R, 4R, 8R, like the 2 power n minus 1 into R. That's why it is called a binary weighted resistor DAC. It is called binary weighted 2, 4, 8, like that. Okay. And another thing is here, why this is MSB. Suppose how to consider the output, one bit at, how to get the overall output, one bit at a time, you should consider. Let us say only LSB I'm taking one and all are zeros if I'm taking, then what is the output? Only LSB, this is LSB, right? If only this I'm taking one, all are zeros, what is the output, you know? Output is what? So V01, let us say. This is what inverting amplifier minus RF by R1 into V input. So minus RF by R1 is what? 2 power n minus 1 into R. R is what? 2RF, right? 2RF into what is V input minus VR, right? That is only connected to this one, remaining all connected to 0. So what you get? Okay, so VR by 2 power n. If only LSB is what to say 1, remaining all 0. The next bit, that means A1 bit is 1, remaining all 0, then what we get? VR by 2 power n minus 1. Like that, the final bit, when the final bit, what we get? VR by 2 power 1 you will get. So that will be the output. So if you see here, so the most significant bit, if you are giving 1 and remaining all 0, so VR by 2 you'll get. So what is the output of DAC? You have to add all, right? So something like this you'll get. So VR by A naught or D naught by 2 power n plus D1 by 2 power n minus 1 plus D2 by 2 power n minus 2 plus so on up to D naught, sorry, D naught, D1, D2, this is Dn minus 1 by 2 is the output. I think this kind of thing we have seen earlier. Okay. Hope you understood. So based on this, you can solve a question. Suppose if you for a DAX, they have given a 3-bit DAC or 4-bit DAC. What is the output reference voltage they'll give? So what is the output? So D naught by 4-bit DAC. Let us say 2 power 4 plus D 1 by 2 2 cube plus D 2 by 2 square plus D 3 by 2 power 1. This is the 4-bit DAC output. This is what R to sorry binary weighted resistor DAC. But the problem here is one thing is it is very difficult to get a wide range of resistances with equal ratio. Like one resistance. Suppose if I want a 10-bit DAC, then what I want R I want 2R I want, like that 2 power 10 into R I want. You got it right? R, 2R, 4R, 8R, 2 power 10 into R. So that is difficult to manufacture this kind of resistances. And also the ratios, if you see any successive two resistors, if you take the ratio should be equal to 2. This 2R by R should be 2. But practically, I think you have seen color coding and all. There will be always some tolerance error will be there, right? So exactly getting ratio 2 between successive resistors is very difficult. That's why this is practically is not preferable. Okay, this is about binary weighted resistor DAC. Is that okay? Any doubts? You can unmute and respond, because I want to cover almost all the things, then solve some problems. I want response. Okay, fine. So let us move on to the next one. Uh, hard to our ladder deck. This question, I think this kind of question earlier we have seen. Here at this, just for example, I'm taking a 3-bit R to our ladder deck. So see, earlier also we have seen why it is called R to R. See here, there is R, here there is a 2R. This is R, there is a 2R. So that's why it is called R to R ladder deck. And this kind of question I have solved earlier. So this is actually, in this we can have two kinds. One is voltage switch DAC, another one is current switch DAC. So voltage switch DAC means it is connected to some voltage, reference voltage VR, and see the last 2R resistance you leave it, and from the next onwards, this is A0, this is A1, this is A2, this is MSB, near to this is MSB, and away from this LSB. The last one, it should be grounded. And here, see, here you will have some switches based on whether it is 1 or 0. If it is 0, it is connected to ground. If it is 1, it is connected to this. Based on this, you will get the we will get the output. We have seen in earlier class also. Suppose if LSB MSB is connected to one, remaining all zeros, how to solve we have seen. R to R, then parallel, this R parallel, so R you will get R plus R to R. So again R to R parallel, R plus R to R, like that we will get, right? We have seen this earlier. Finally what you will get, some Thevenin's equivalent and Thevenin's resistance will get. What we get here, some 3R will get. See here VR by 2 will get. So for MSB, let us say V02, what I get is VR into A2 by 2. A2 is 1 or 0 based on that. Similarly, V01, the next bit for A1, what you get is VR by you. We have discussed this kind of problem, A1 by 2, sorry, 2 square. And for LSB, VR into A0 by 2 cube. Like this you'll get. So overall is what? Something like this. You have to add all of them. So overall is, like earlier only we have seen. I think I did not miss anything. Yeah. So overall, if you take VR into V0, sorry, A A2, let us say 4-bit. You take A2 by 2 plus A2 by 4 plus A1 by 8 plus A naught by 16. So here if you see LSB less weightage by 16, MSB more weightage. This kind of problem we have seen earlier also. So I think if I show that problem, you may remember this one. You see, hope you remember this. Using the same formula, see here, it is anyway each showed the from here you can start from here. This is A naught, this is A1, this is A2, this is A3. It's a 4-bit DAC, R2R ladder DAC, and this is one. Sorry, connected to ground 0. This is connected to plus 16. So this is 1. So 0. Sorry. This is 1, and this is 0. So what is the output? We said V R into A3 by 2, A2 by 4, and A1 by 8 plus A naught by 16. This is what we'll get, right? This you can extend to anything. So this is the MSB and this is the LSB. So this I think we have solved earlier. Quickly let us solve. So 1.6 is the reference voltage, 1.6 into A3 is 0 and A2 is 1, right? So 1 by 4 plus A1 is 0 and A0 is 1. So 1 by 16. This is 1.6 into how much you'll get? 5 by 16. So what we get? Minus 0.5 we'll get. Since it's a minus sign is there, this is inverting amplifier, right? It's an inverting amplifier. Definitely there will be a minus sign will be there. Minus 0.5 volts. Is that okay? Yes, sir. Yeah, fine. So this we have seen, and but the problem here is, and also for any DAC, if they asked you to find out what is the step size or resolution, if they ask step size or resolution, if they ask what you need to do, I already told, right? You keep only the LSB one you keep and all other bits zeros you keep. You find out the output. That is nothing but the resolution. Okay. And what is the full scale output? That is also you keep all ones, then find the output. That is the full scale output. Okay. Full scale output we have seen, right? 2 power n minus 1 into step size. Okay. But the problem in this is only here we are using two resistances R2R only. Earlier we want R2R, 4R like that, 10,000, 24R like that. But only R2R somewhat okay. But here it is voltage switch DAC. Here based on the voltages, if it is one high voltage, zero low voltage we are giving. Sometimes you may get some unwanted spikes at the input that will disturb the output. That's why it is to overcome this we go for current switch DAC. It is similar to voltage switch DAC. This is the current switch DAC, you can see. Okay. Now in current switch DAC, this kind of arrangement will be there. Anyway, it is a voltage source only, some reference voltage, and it is connected at this one, a non-inverting terminal. So this is the arrangement. So if it is see here, if it is some particular bit, if it is 1, then it is connected to this one. If it is 0, connected to ground. But one thing is which is near to the op amp, that is LSB, which is away from op amp, that is MSB. In previous case we have seen in the which is near to op amp, that is MSB, and away from op amp, that is LSB. Okay. For this also we can easily find out the output. This is standard one. This you can extend to any number of bits. Let us say I is the current coming from here. How to find out the current? How much current is there? The same current will come here. So you know, right, using virtual ground concept, if it is 0 here, if op amp is ideal, here also 0 you can say. And based on this, you can find out the resistance of this entire circuit, right? What is the equivalent resistance of the circuit? These two are parallel, these two are parallel, then R will get R plus R 2R, this series, then parallel, something like that you'll get. The current is some VR by R you will get. Okay, current is what? VR by R you will get. Fine. Now if you see here how the current is divided between them. Yeah. See here, this is MSB, right? This is MSB away from this. If you see here, the current have two paths here. The current have two paths here. One path, two path. So here, one path, the equivalent resistance is 2R. So anyway, it is virtual ground concept. This voltage also zero volts. And another side you take, let us say all are connected to this. Another side you take. Now if you see here, these two are parallel, R. So this and this are series, 2R. Again this two are parallel, R plus R 2R. So overall you'll get 2R. So the current is facing equal resistances, 2R 2R. That's why it will be divided into equally, I by 2, I by 2. Similarly, this I by 2 is coming here. It will be divided as I by 4, I by 4. Like this again, this I by 4 coming, it will be divided as I by 8 and I by 8. So all these currents will come. What is the I dash? Let us say this is I dash. Now what is output of this inverting amplifier? Minus I dash into RF, right? This inverting amplifier minus I dash into RF. What is I dash? So I dash is, so RF into what is that I dash? I by 2, I by 4, I by 8, it is dividing, but based on the bit. If it is 1, then the current will not enter here. If it is current enters a op amp, and if it is 0, it will not enter, right? Can I write like this? So A2 into I by 2 plus A1 into I by 4 plus A0 into I by 8. Can we write like this? Because if it is A2 is 0, then that current will not come, right? The current will go into ground. If A2 is 1, then only it will contribute to I dash. You got it right? So the advantage is any spikes present at the input will be eliminated. That's what. So the output is the I you can find out like this. The whatever voltage is there and the R equivalent you have to find out. This equivalent resistance you have to find out. And as I said, based on number of bits, I dash is what? Some an minus 1 by 2 plus an minus 2 by 4 plus so on plus a1 by 2 power n minus 1 plus a naught by 2 power n, like this into. You got it right? This is about the current switch back. Understood?
So can you zoom that image?
This one? Yeah. Which is nearer to the DAC, that is LSB, because less current is passing. First I by 2 is dividing and I by 4, I by 8, like that. Which is away, that is MSB. Okay.
Yes, sir.
Fine. Based on this, I think some question was given some time back. Yeah, this was given in 2007. Um, so in the digital to analog converter circuit shown in the figure below, okay, VR and R are given. Then what is the current I they are asking? The same the DAC, whatever we have seen just now, right? Right? That is the total current is this, and you try to find out the equivalent resistance now. Total current is I. Now what is total current? The VR by R equivalent, total equivalent resistance. Now, if you see, due to virtual ground concept, this is op amp, right? We assume ideal, so it's negative feedback is there. So this is also 0 volts. So all are like connected to ground, right? All resistances. Now these two are in parallel. So equivalent resistances are again R plus R series. Equivalence resistance here 2R you will get. Again these two are parallel. R you will get R plus R 2R. Again 2R we are getting here. Then these two are parallel R. So R plus R 2R we are getting. Now these two are total R. So equivalent resistance is R we got. So V R by equivalent resistance is R. What is the current here? 10 volts by 10 kilo. That is 1 milliampere. That is the current I here. But what they are asking, the small I they are asking. This current they are asking. Small I. So just like that we have seen, right, how it divides we have seen. So here it goes divided as I by 2, I by 2. Again I by 4, I by 4, I by 8, I by 8. And here finally I by 16. And what is this I by 16. Like that it divides, right? I by 2, I by 4, I by 8, I by 16. So what we want is I by 16. So the required current I is I by 16. I by 16 is what? So 1 milli by 16. So 1000 micro by 16. How much? Around 62.5, 65 something you'll get micro amperes. I think 62.5 micro amperes. Is that okay?
Yes, sir.
Yeah. Once you know the concept behind that, then you can just play with this. I think another question also. Let me take. Uh, this is in GATE 2015 they have given. So what they have given is consider a 4-bit DAC. Okay, 4-bit DAC. 4-bit DAC. The analog value correspond to digital signals of values 0000 is 0. When you are giving 0000, output is 0 volts, and when you are giving 0001, output is 0.0625 volts respectively. The analog value corresponding to digital signal 1111. That means what? When all zeros, zero voltage is there. And this is what, when 0001 output is, this is step size, right? Yes sir, no? So what is the output? Any output you can calculate. Actually, they are asking full scale output, right? All four ones means definitely it is full scale output they are asking. So 2 power n minus 1 into the step size you can find out. 2 power n minus 1 is 15. 15 into 0.0625 something. Or suppose if they are asking when it is 1001, what is the output? The decimal equivalent you find out for this. What is the decimal equivalent? 9 into the step size. So 9 into 0.0625. You got it right? The decimal equivalent into step size resolution. Okay. Hope no doubt in that. Then we will see about digital to analog converters. Sorry, analog to digital converters. So far we have seen about DACs, right? Digital to analog converters, which takes an digital input and gives analog output. Now we will see about analog to digital converter. So what is the input to analog to digital converter? Actually, you will have input signal, then it is sampled, then quantized. That sample only will give as input. Okay. So in this, as I said, we have like different types of DACs. So one of the ADCs, one of the ADCs, counter type ADC we'll see. So in counter type ADC, this is the rough circuit you can see here. The counter type ADC. Okay. So if we can see here, the sample value will give as input to the DAC. So here, so the DAC is having, sorry, ADC. ADC is having an n-bit counter and also a 4-bit. Let us say if it is a 4-bit one, you will have n-bit ADC, means n-bit DAC also it will have, and also you have a comparator and some logic circuit. Okay, and if you see here, this is the digital output of the ADC. For the ADC, counter type ADC, this is the digital output. You will have some other control. Reset means the counter will be reset to 0. So at for this, hope you can see this. I'm zooming it. For this comparator, the DAC, digital to analog converter output is given at the inverting terminal, and actual our sample is given at the non-inverting terminal. Okay, whatever sample we want to convert into digits. Let us say our sample input Vin is, let us say, some 4.8 volts. I'm giving 4.8 volt, that we want to convert into bits. Okay, that means I am giving a sample value is 4.8 volts. Okay, now the comparator output, you know, right? The comparator output is either high or low based on inputs. When Vin is greater than Vd, that is a DAC output. I am telling Vd, so this is Vd, so this is Vin. When Vin greater than Vd, output is 0. 1. When Vin less than Vd, output is 0. You got it right? Now this P, let us see the output we are saying P. This P is given as input to the gate, an AND gate. Now when P is 1, the clock will reach the counter. So one input of this AND gate is clock, another input is the this one, this output of this comparator. So when it is 1, P is 1, the clock pulse will reach the counter. The counter will be incremented. You know, right? Based on the clock pulses, the counter value will be incremented. And counter will be incremented. And the output of the counter is nothing but our DAC output. Now, also the counter output is given as input to the DAC. The n-bit counter output is given as input to the DAC. Now the DAC will convert that voltage into, sorry, that value into an analog voltage, just now we have seen about DACs, digital to analog converter. Now again it compares, based on that the P value either 1 or 0. When what happens when Vd greater than Vin, when this reaches, when Vd greater than Vin, what happens? The output of comparator will become 0. When the output of comparator is 0, then what happens here? The AND gate input is 0. When AND gate input is 0, then there will not be any clock pulse reaching the counter. Then the counter stops here. The counter stops here. And the stopped value, that is nothing but the final converted value of the ADC. You got it right? Fine. So this is about a counter type DAC. Let me take an example. I said V in is 4.8 volts. Initially, I reset the counter. First, what you do, you will reset the counter and you will start. You have resetted the counter. The counter input is 0. The counter output is 0, 0, 0, 0. And you have input you have given 4.8 volts. Okay. Input I have given 4.8 volts continuously. I'm drawing here. Somewhere here input is not 5, 4.8 I'm giving. Okay, 4.8 volts. Input constantly I'm supplying at the plus input. Now counter initially reset. So what is the now counter value goes to the DAC. What is the DAC output? DAC output is 0. Now, since DAC output is 0, Vd is 0, Vin is 4.8, so P is 1. So P is 1. So the clock will reach here. P is 1. The clock pulse, first clock pulse will reach here. So counter will be incremented 1. Counter will be incremented 1. What is the output of DAC? Output of DAC is, step size is 1 volt. So output of DAC is 1 volt. So 1 volt. This is output of DAC I'm drawing. Okay. Next is what? Still it is 1, but input is 4.8. Still P is 1 only. So P is 1 only. The next clock pulse will reach. Quickly I am explaining. So counter will become 0 0 0 1. So 1 0. So the corresponding this one is what? Here output you'll get 0 0 1 0. It's a 4-bit DAC assume. The corresponding output of this one is what? 2. Still P is 1 only. Like that it will go. The VD DAC output will increment. VD like this. 3 volt, 4 volt. Okay. Now the next 4 volts. Next what? Again one more clock pulse entered. So fifth clock pulse came at the input. Now the output of DAC is what? 0 1 0 1. So counter is 0 1 0 1. Now DAC output is what? 5 volts. 5 volts. Now our input is 4.8 volts. DAC output is 5 volts. So what is the P? Output of comparator will become 0. So the AND gate input is 0. So how many clock pulses you apply doesn't matter. The clock pulses will not reach the counter. That means only first 5 clock pulses reached. That means the counter stops there. So that is nothing but our output 0 1 0 1. You got it right? The counter stops there because afterwards it cannot increment. Okay. So what is the value of the counter here? If you can see what is the value of the counter, input voltage by step size, the ceiling value you have to take. I have taken 4.8, right? So what is the input voltage? Input voltage is 4.8 volts, step size 1 volt, ceiling you have to take. So this is 4.8, ceiling is how much? 5 volts, integer value. Sorry, 5 volts. It's corresponding, this one is nothing but that means 5 is the value of the counter. What is the output of the DAC now? That 5 we express in terms of 0 1 0 1. Okay, if it is 6.3 input, so 6.3 by 1 is 6.3. Ceiling is what? 7. 7 is the value of the counter decimal. If you express in this one, sorry, DAC output is 0 triple 1 if it is a 4-bit counter. Okay, you got it right?
Can explain how it is selling.
Ceiling means the see, it's like upper value. See, because 4.8 volts I'm giving, but when you're getting 4 volts, still the counter is incrementing. Na? When it is 5 volts, then only it is not incrementing, right? The next integer, ceiling means the next integer. Suppose 4 point, let us say 9.8 means ceiling means next integer 10 volts or 10. You got it right?
Yes, sir.
Okay. Fine. Now, one thing I want to ask is here, like what will be the maximum conversion time? That means first you have given one sample here. Let us say different samples I want to give. First I have given 4.8, next maybe 6, next maybe 8, next maybe like this a sine wave kind of a different samples I'm giving. Let us say this is a TS, time period between the samples. One after another samples will come. So what should be the spacing between the samples? What should be the spacing? We need to see what is the maximum conversion time of this counter, right? What is the maximum conversion time? If it is a 4-bit DAC, it can go, if step size is 1, it can go up to 15 volts, right? You got it right? So what is the maximum conversion time? Maximum conversion time, T max, is what? 2 power n minus 1 into the clock period, right? That many clock pulses are going, right? 2 power n minus 1 into clock period. Have you understood?
Yes, sir.
If it just I'm giving 4.8, then only 5 clock pulses it is taking. So each clock pulse duration is, let us say, TC. Each clock pulse duration is TC. Then what? 5 into TC. Suppose if I am giving 12.3, then 13 into TC. Like that maximum you may get 14.8. Full scale reading is 15, right? 14.8, that means 15 TC. So maximum conversion time is 2 power n minus 1 into clock pulse. So this is the problem here. So much conversion time. That means sampling interval, the next sample should come only after this time. Okay, then the next sample should come only after 2 power n minus 1 into a TC clock pulses. Understood, right? This is the problem here. Somewhat it takes more time for converting each and every one. You got it, right? Suppose what happens if it is a 4-bit counter, then what is the 4-bit ADC? Then you will have 15 TC. If it is a 5-bit ADC, let us say 5-bit ADC, then it is what? 5-bit ADC is what? So 31. 6-bit means 63. That means for each bit increment, the conversion time is doubled almost. If you can see here 15 into 31, 31 into 63, that means almost the conversion time doubled. So that is another problem. If you use counter type ADC, that is another problem. Okay, the conversion time doubled for every 1-bit increment. Got it, right? So based on these concepts, you can apply the concepts to solve any question. Okay. If you have don't have any doubts, we quickly move on to the next topic. Next, can I move on? Yeah, fine. Bunty, are you getting? I think you have asked, right? Are you go?
Yes, sir.
Yeah, I'm not touching this successive approximation counter because time is not there, and but this is important. Later you can see because whatever questions I got from previous years, based on that, those only I will touch. Now I'm not touching successive approximation counter due to the time constraint. The next one is flash ADC or parallel ADC. Okay, flash ADC or parallel ADC, analog to digital converter. Flash or parallel. It's a 3-bit one, for example, I'm taking. So you have a priority encoder here. You have a priority encoder and you have comparators. You know comparator, what is a comparator? Op-amp comparator. And for an n-bit flash ADC, how many number of comparators required means 2 power n minus 1 number of comparators are required. So if it is a 3-bit, so 2 cube minus 1, 7 comparators are required. And the priority counter, that kind of priority counter should require. So if it is a 4-bit one, 15 comparators are required. And priority counter input, sorry, priority encoder, not priority counter. It should be actually the sessions I am recording and I'm giving to NPTL. Just you can ask from NPTL. Otherwise, I can upload in YouTube because if you can ask from NPTL, I think they will upload or else I can upload if they say yes. You students request them. Okay, all the sessions are there with me recorded ones. Okay, so if you see here, the D0 is connected to ground. Let us say this 8 to 1 priority encoder. Sorry, 8 to 3 priority encoder. So D0 to D7. Lowest bit is connected to ground, and each one is connected to a what to say a comparator, and you have a potential divider arrangement like this. So V in whatever sample value we want to give, let us say that is some 4.8 volts, let us say that is given to all the plus inputs of the comparators. You can see, and you have a potential divider arrangement. You will take some reference voltage here, and that is what to say divided between them, and that is given to the not inverting terminal of the what to say comparators. Okay, for plus terminals of the plus input terminals and non-inverting terminals, V input sample value is connected, and minus terminals the through some potential divider arrangement we are connecting here. If we can see here how many resistors are there, one, two, like that. So how the voltages will be divided means, you can see here, if it is, this is VR, you can check later, this will be is 1 VR by 8, VR by 8, because how many resistances are there, you can check, total 8 resistances are there. So VR by 8 here, 2 VR by 8, 3 VR by 8, 4 VR by 8, 5 VR by 8, like that. This is 7 VR by 8. You got it right. This is the whole structure of a flash ADC. You have a priority encoder. The LSB of the encoder is connected to ground, remaining all connected to output of the comparators. And for all the comparators, common input voltage is given plus at the plus terminals. And through a potential divider arrangement, you are at the inverting terminals. We are dividing the voltage and giving. Okay, now let us say I am giving some input voltage that is in between 4 VR by 8 and 5 VR by 8. For example, I am giving an input voltage that is between 4 VR by 8 and 5 VR by 8. That means somewhere here 4 VR by 8 and 5 VR by 8 in between. Now anyway, D0's input is 0 since it is connected to ground. Now up to here, input voltage is between 4 VR by 8 and 5 VR by 8 I'm giving. So if we see here, for the first comparator, what will happen? From the down, the seventh comparator, you can say, for the seventh comparator, so definitely it is VR by 8 at non-inverting terminal, and inverting terminal, it is greater than 4 VR by 8. That means positive is greater than negative, so output is 1. Similarly, for the second one, also output is 1. Third one also 1. And fourth one also 1, because we are giving input greater than 4 VR by 8. Fourth one also 1. Now, output of the fifth, this third comparator, you can say. Anyway, numbering maybe volta have given, that is okay. For this, you see, here input is what? At the non-inverting terminal input, what we are giving for that comparator? 5 by 8 VR, and at plus input what we are giving, that is less than 5 VR by 8. Now what will happen, its output is 0, right? So its output is 0, and remaining all upper comparators outputs are 0. You know the comparator rate, which one is greater, based on that output is 0 or 1. Okay, now since it is a priority encoder, you know how many number of inputs are 1, that doesn't matter, which is the LSB, MSB, most significant bit will be considered. If you see here, for the priority encoder, D1 is 1, D2 is 1, D3 is 1, D4 is 1. But in this, which is having most priority, D4 is having. Only once you consider which is having most priority, D4. The 4 will be converted into digital output, right? 4 is what? 100. Hope you understood. 4 is 100. If I'm giving input somewhere in between 6 VR by 8, less than V input less than or equal to 7 VR by 8, then 6 and 7 between here, till here I think till D6 we, we will get ones and remaining all zeros. So D6 will be encoded, so output will be 110. Okay, this is about a flash ADC or parallel ADC. Okay, now if you see here, some points I want to stress here. Now you no need of any clock pulses here. Just you give the input or reference voltage, you switch on the circuit, immediately you'll get the output. Okay, you neglect the delay of comparator, neglect the delay of priority encoder. So immediately you'll get the output. That's why it is called flash ADC. Immediately you will get the output. That means delay is reduced. The samples can be arrived like very immediately, the next sample can come. Okay, there will be some delay for the priority encoder, also for the op amp, you neglect that, otherwise there will not be any what to say, a clock and all. So earlier counter, we need to wait for how many clock pulses, 2 power n minus 1 clock pulses, but here doesn't matter. But the problem here is, For n-bit counter, how many comparators required? 2 power n minus 1. 3-bit counter, 7 comparators required. If it is a 10-bit counter, 1023 comparators required. That is highly impractical. Having that many comparators, it will make the circuit complex and costly. That is the problem here. Okay. So, okay, the next session is going to start. Who wants to go to there? They can go to that session. I'll just finish this topic and one, two questions I'll solve and stop here. Okay. So that's what I was telling. If the input is between 4 VR by 2, 5 VR by 2, these are the inputs of the priority encoder. This will be encoded. If it is between 2 VR by 2, 3 VR by 2, these are the inputs of priority encoder. This will be encoded. D2, right? So 0, 1, 0 like that. Okay. So that's why this is the fastest of all comparators. Sorry, not comparator. Fastest of all ADCs. Okay. Now, based on this, we will solve one question. Who wish to go? I mean, the next session you can join. If you want to stay back, you can stay back here. One, two questions I will solve here. Then stop. Yes, I think this we have covered. This we have covered. Yeah, this we have covered. This question will solve. You see here. This was given in GATE 2016 for 2 marks. Yeah. In this, you see in an n-bit flash ADC. Okay. Flash ADC, the analog voltage is fed simultaneously to 2 power n minus 1 comparators. We have seen V input is given simultaneously to all the comparators. Okay, that we have seen V input is given simultaneously to all the comparators. The output of the comparator is then encoded to a binary format using some digital circuits, priority encoder. Assume that the analog voltage source Vin is having source resistance of 75 ohm. So this having some source resistance of 75 ohm as shown in the circuit, and the input capacitance of each comparator is 8 picofarad. Each comparator is having 8 picofarad of input capacitance. So each 8 picofarad. The input must settle to an accuracy of 1 by 2 of LSB. Okay. Even for a full scale input change for proper conversion. Okay. Even for full scale input to conversion also, it should settle at 1 by 2 LSB. That we'll see what is that. Assume that the time taken by the thermometer to binder encoder is negligible. This one, these things are negligible. Then if the flash ADC has 8-bit resolution, that means it is a 8-bit flash ADC, n equal to 8 they have given. Which of the following alternatives is closest to the maximum sampling rate? So what they're asking is, what should be the sampling rate, maximum sampling rate? That means what should be the minimum interval? Sampling rate is Fs rate. What is F max? F max is 1 by Ts. That means Ts minimum they're asking. What is the time period between the, first we need to find out time period between the successive these ones. That means we need to find out the conversion time of the comparator. We need to find out. That's what, right? That is that based on that sampling period should be greater than conversion time of the conversion time of this ADC, and then based on that we can find out Fs is 1 by Ts. That's what they're asking. And quickly I'll give the hint. Now if you see here, n 8 n equal to 8, that means how many comparators are there? 8 comparators, sorry, 2 power n minus 1, 2 power 8 minus 1, how many? I think 255 comparators are there, and all these comparators are in 250 comparators are there. Now each is having some capacitance 8 picofarad. Now all these are parallel, right? If you see, parallelly input source is parallelly connected to all the comparators, just like we have seen here. Yeah, here parallelly connected, right? Input to all the comparators. That's why. That's why they are parallel. The capacitors are added. So C equivalent is what? All are added. Each one is 8 picofarad. And how many comparators are there? 255. All are added. That's why I'm multiplying. Okay, parallel. R are in parallel. What is the C equivalent? 255 into 8. Around how much? This is 2000. Nearly I'm writing into 10 power minus 12 is what? 2 nanofarad. 2 into 10 power 9 minus 9 farad. Okay. Now you have voltage V in here. You have source V in here. It is having source resistance here. And all the comparators, what to say, this capacitance C equivalent I'm representing. It is 2 into 10 power minus 9 farad. Now immediately whatever input voltage you are giving, immediately it will not go to the this one, because since because of capacitance it will slowly rise, right? The input voltage at the input of comparator slowly will rise exponentially. It increases with what time period? Tau equal to rc. RC, right? Time period. So 75 into 2 into 10 power minus 9 is 150 into 10 power minus 9 is the time period. This with this much a time period it will rise immediately. It will not rise. Now our capacitor you are applying, let's say full scale reading you are applying at the input. So what is the full scale reading here? So 255 into step size, let us say you are applying full scale reading. So what is that? That is the full scale reading. That means full scale reading is nothing but Vn, whatever input voltage I'm giving. Now they are asking it should be settled below 1 by 2 LSB. That's what that much error is, you can say. That means input must settle to an accuracy of 1 by 2 LSB. What is a LSB? Well, LSB is nothing but step size only, right? Half of step size you can settle. That much error can be possible. So what is the step size? V in by full scale reading by 2 power n minus 1, 255. This is the step size, right? So that means 1 by 2 into this one. So V in by 510. This much error can be possible. That means the capacitor voltage charging, let us say V in is this one. Slowly the capacitor voltage rises. That means input voltage, because of capacitance, whenever you give input, suddenly it will not go to the comparator input. It will slowly rises. So this much error can be possible. Step size by 2 can be possible. That means what? Maximum how much time it takes? Maximum is V in we want. So V in minus half LSB. This much the capacitor has to charge. So that is V in minus V in by 510 or something. Yes, this one. That means the capacitor voltage charging from zero, starting from zero, and it can go up to this one. This I say final voltage. Zero is the initial voltage. Now you know, right? When the capacitor is slowly charging, you might have seen what is the VC of the capacitor voltage? V final plus V initial minus V final into e power minus t by RC, something like that you might have seen, right? So what we want till here we want. So the voltage is how much time it takes, that's what we want for charging this one V in minus half LSB. So for charging this one, what? V in minus V in by 510. So V final it can go up to V in, right? V final is V in, V initial is 0, again V final is V in into e power minus t by RC. That much time is required to charge that one. Okay, this is the this up to this voltage it is okay. V in minus half LSB, half of step size we can have the error. So final it can charge up to capacity. These things low pass high pass circuits. Final it can go starting from zero. RCVL we are already having how much time constant? Some 2 into 10 power minus 9 we have seen. From this you find out T. Okay, that means that much time it takes. That means between successive samples, this much time should be required. Okay, that means what is the frequency? This much time should be required between successive samples. So between successive samples, TS minimum, whatever T we will find out here, that much is required. So what is the maximum sampling rate they're asking? 1 by T. You calculate it, I don't remember the number, but you calculate this from this. So 1 by t you find out that is the maximum sampling rate. From here the answer for this 1 mega sample per second, that means 1 mega samples per second, that many you can give. 1 mega means fsc is what? 1 mega 10 power 6 samples per second. That means what is the minimum sampling rate, minimum time period between the sampling interval? 1 by 10 power 6. That means 1 microsecond. That means between successive samples, at least 1 microsecond interval should be there. Then only we can convert the samples. You got it right. Basically, it is depending on the delays. Even the flash ADC will not have any delay, but still the components will have delay. It acts like a RC high pass circuit, right? High pass or low pass. So series resistor and a capacitor. So this acts like, I think, a RC low pass circuit. That's why whatever input voltage we are applying here, immediately it will not go to the comparator input. It takes some time. How much time it takes means, we have to consider always the worst case scenario. The worst case scenario is full scale output, that is VN. So they are allowing half LSB, half of the step size they are allowing. So that's why based on this we can find out the time, and based on that we can find out the sampling interval. You can check it. You can resolve this question. This was given in GATE 2016. Okay, based on whatever we discussed, you can easily solve this. Okay. Resistor doesn't matter here. Whatever may be the resistor. Resistor they have given. Sorry, 75. Internal resistance of the source. The source resistance is 75. All the each comparator is having. They said how much? 8 picofarad. All are in parallel. So 8 picofarad into 255. That is the C equivalent. So tau is R into C equivalent. 75 into 2 picofarad. Okay. You can try to resolve this, but I could not cover the other ADCs, dual slope ADC and delta sigma ADC. But if time permits, would have. Fine. Any other questions from you? Okay. Gopinath and Kushbu, any doubts from your side?
sir.
Fine. Hope our our session somewhat helpful to you guys, and all the best for your gate exam. Do well in the exam. All the best.
So much, sir.
Yeah, we'll stop here. Yes, thank you. Thank you all.